Okay, maybe. So there are a couple, like I think I warned you, there were a couple that I gave you that you have to do several applications. If you go to the tutors, I can't blame the tutors for this. They will tell you, and we're going to talk about it today. I've got a little handout I've got a little thing about how this works. There's things called binomial CDF and binomial PDF in your calculator, right? Magic buttons that do something inside of their magic little black box, and then it spits out the right answer at you, and you've learned nothing. So I have no problem with showing you that and letting you check your work using that, but that's not your work, right? So I always get at least one person that writes down on a quiz or something, I pushed this button, and then I got this. That's not work. That's not work. Okay, maybe. All right. Really sorry. You picked the wrong teacher if you wanted to push a button and get through the class. Teacher, it's not me. Anything else from homework stuff? Anybody? Right now, you should definitely be part of the way through chapter 4 at the least, right? You should be getting into 4.2 if not done with 4.2. Yeah, because what did we do last time? Do you guys remember? I forgot. Chapter 5, which was? What am I doing?
Oh, uniform distribution.
Uniform distribution, right? Which is just one big ass rectangle, correct? So we're going to do a few examples of that. I haven't shown you something. What did I tell you guys? Every time we get a new way to be given data, so when we had data given to us as x p of x, we figured out the mean and the standard deviation formulas, right? You guys with me? Mean is sum of x p of x. Remember all that business? And I try to say then, every time you're given data in a different way, we want to figure out how do I know the mean and the standard deviation in this situation. Those are the two most important summaries of data. What's the middle? So the mean kind of wins. What's the spread? Standard deviation, right? So we just learned a new way to be given data. Uniform distribution, correct? And we haven't talked yet about how to find the mean and the standard deviation. I know some of you guys are like, I am fine if you never tell. I will tell you this. You're going to see it in the homework. You're going to need to be able to plug stuff into the formulas, but I am not going to use the formulas much. They don't come up very often, but I want you to know they exist. So they are in the homework. So let's do that first if there's no more questions about anything from homework or anything. Okay. Anybody not get their quiz back yet? Okay. Yeah, I came all the way. So real quick, what you'll see in the book loves to use this kind of notation. So what do you think this means? Uniform, I love it. So another one you'll see is like B something. What do you think that means? Binomial, kick ass. What do you think 7 and 19, what's the most important thing to know about a uniform distribution? Okay, good. So the general concept is it's all equally likely, so you get a nice flat top. But what's the most important thing to be able to graph it correctly? You want to know where it starts and ends. So that's the two things they'll tell you there. So so take a minute, draw the uniform distribution that starts at 7 and goes to 19. And I'll catch up to you.
It's part of the 5, right? Chapter 5 notes?
Yes. All right, I'm going to catch up to you. So it should go from 7 to 19. So this is not a complete picture yet, right? What am I missing? The height. Making it 1. So what would make it 1? So how wide is this? 12. So how tall must it be? 112. Cool. Does that make sense? Remember, if I have a visual and I make the area 1, then any slice that corresponds to a question, the area of that slice is the answer to the probability question. That's kind of too nice to believe. It just, for right now, it's too nice to believe because we got freaking rectangles. So when I'm talking about area, those are cool. When I got a graph like a normal distribution, the sides are going to be weird as shit. It's going to be like the melted crayon thing, right? We don't have a geometrical formula for a melted crayon that I know of. So let's just deal with rectangles for the moment. So now we got that set up. That would be like part A. Graph it, showing the height. Part B would say, what's the probability that I get between 12 and 15? Bless you.
Would it be
3
times 1? Well,
Yeah, so if you cut that slice out, so here's about 12, here's about 15, it doesn't have to be perfect. That's the area I want, so area is the same thing as probability. If you make your total picture equal 1, so that is 3y times 1/12, 3/12, 1/4, 25% chance. Somebody remind me real quick. Binomial, by the way, binomial, just to complete this idea. What are the 2 most important things for me to tell you about a binomial probability distribution? Think back to the problem with the questions. The most important thing you had to know was
2 numbers.
2 numbers, and what are they? Binomial distribution. What are the variables associated with binomial? I'll get us started. N, P, Q, X, right? X, what did X mean again? What does X mean? I love you guys. You're all like, just tell me, man.
How many successes?
Yes, number of successes. Look at this. I love this. She's like, I wrote that shit down. This is not a quiz. You can look at it in your notes. So X is the number of successes. That's going to be the question, right? So I don't need to know that just to set up, just to have an idea of what the distribution is. I need to know N, and I only need to know P. Because of course, if I know P, do I know Q?
Yes.
Because they have to make 1 together, right? So for a binomial, they're going to give you N and P. Okay, lock it. So coming back to this, can anybody tell me the main difference between a binomial and a uniform, besides the shape of it? Because binomial, for example, 32 questions on a quiz, and I want to know what's the chances I get so many right. How many could I get right? All 32, or 0, or 1, 2, 3, 4. Okay, good. You with me? What kind of data is that? 0, 1, 2, 3, 4. Is that discrete or continuous? Discrete. What kind of data does this represent? All right. So this could be like ages, this could be time. What kind of data is time or age? Continuous. Right? Thankfully, you don't wake up in the morning of your birthday and you instantly age a year. You just continuously are aging, right? You wake up and go, ooh, Not all of a sudden anyway. It will happen. Okay. I guess somebody with me. So there's a point I'm getting to. You got to know all this shit, but it's specifically for this next question. What is the probability X equals 11? Now, before you say anything, how did we calculate part B? How did we calculate that? We found how did we calculate part B? Where did it come from? Where on the picture is it? The shade, right? The shaded part. So we found the area of that, correct? Okay, now think about question C. Why?
Oh, wait, is it using the question number 1? Like,
No, it's its own question. It's its own question. let me erase this out of here.
So 11's replacing the 3.
Where's 11? Here, is that okay? 11. What's the area of what I just drew in? How wide is 11? It goes from 11 all the way up to 11, correct? So how wide is that? 0. Times, I don't care what the height is, that's going to be 0, correct? Real quick, why does that make sense? Guys, I have a bag with 100 chips in it. One of them is white. What's probably pick out a white chip? 1 out of 100, 1%, kick ass. And then what if I have 10 million chips? One of them is white. What's probably pick out a white chip? 1 out of 10 million, or whatever it was I said, right? I'm with you. You with me? Isn't that much smaller than the 1% when there was only 100? Yes. So what if I let the number of chips in my bag go to infinity? And I got one white chip in there. Probably pick out the white chip. It's basically 0. 1 over 100 is much bigger than 1 over 10 million. Do you guys agree with me? Which is much bigger than 1 over 10 million to the 10 millionth power. You guys with me? Which is much bigger than 1 over 10 million to the 10 million to the 10 millionth power. I mean, I have no limit on how big I can make the denominator, but when I do 1 divided by that shit, it's getting small quick. Yes? You guys sort of with me? Since there's an infinite number of possibilities, could 8.394 happen? Yes. Could 9.222227 happen? Yes. Could the square root of 81.72 happen? Yes, because it's between 9 and whatever, so it's in here. So there's an infinite number of things that can happen, right? So what's the probability that any specific thing happens is 0, because there's an infinite number of things that could happen. Does that make any sense? If there were 100 things, 1 out of 100. If there are 1,000, 1 out of 1,000. If there are a billion, 1 out of a billion. Each time I make the bottom grow, the result gets smaller. There's an infinite number of things in there. Is everybody cool with just that? Right? You guys are cool with that? There's an infinite number of numbers between 7 and 19. Okay. But a much easier way to look at it than all that shit I just said is the answer to a probability question for a continuous thing is just the area that it carves out. Is the area the question carves out. Well, when I draw that question, there's no area. It's got no width. So that's why it's 0. Okay, maybe. I pushed it in my other class. Is everybody semi-cool with that? The answer to a probability question is equal to the area the question carves out. Isn't that exactly what we did for part B? Yes? Man, you guys look really,
Would it
some of
be
you guys look really sad.
Would it be the same if the numbers, let's say it's between, I don't know, 8 and 7 and 8?
No, now it's between. Now it's got a width. Right? So let me draw, here's what part B looked like. Remember, here's what part B looked like. It was from 12 to 15, right? Is there an area there?
Yeah.
Is there a width? Is there a height? Yes, totally.
No, I'm saying, you know how the 7 and the 19, let's say it was a 7 and an 8. And
Yeah, so if the
7
question
and a
was,
half.
was probably that it's between 7 and 8, does that make an area?
Yes.
Totally. That is a very different question from this, right?
I think
Here I start at 7 and I go to 8.
yeah.
I think what she's trying to ask is instead of 19, if it was 7 and 8.
And then let's say the x is like, I don't know, like 7 and a half. Would that be still 0?
What would the question be exactly?
So instead of uniform distribution of 7 and 19, it's uniform distribution of 7 and 8.
And then
Oh.
x would be like a 7 and a half. Is that a thing?
I see, okay, well, all right, let me make sure I understand the question. So you're saying, what if I had a uniform that went from 7 to 8?
Okay,
Okay.
and then
And the height would be 1, is that cool?
mhm.
How wide is it? 1. What's 1 over 1? 1, kick ass. And then I asked you, what's probably x equals 7.5?
Yes. Would that still
It
be
still
0?
has no area, correct? It still has no width.
Still 0.
You guys see that? Real quick.
So since it has no width, you're just multiplying it by 0, so that's why it's 0.
That's it. That's all I'm saying. That's the easiest way to look at it is, if the answer to a question, when I have a continuous distribution is the area carves out, and the question doesn't carve out any area, the answer is 0. You guys with me? Okay, maybe. All right. So what about this one? What's the probability x is less than 7? Zero. Why? Because that's out of the range of what could happen. What's the only stuff that could happen in this problem that they gave you?
7.
From 7 to 19. So what's probably something below 7? It's sort of like me saying, roll a die. What's the probability I get less than 1? You're like, let me look at the die. What the hell are you talking about? So it's a normal die, right? Probably get less than 1 is 0. Because it only goes 1 to 6, right? Okay, maybe. So that's also 0. What about the probability x is less than 19? 100%, because that's the whole damn picture, right? Less than 19. Now somebody this morning said, doesn't that leave out 19? It does, but what's the probability x equals 19? 0. So that doesn't add anything, so that's everything, yeah. Okay, maybe. So there are like a couple of little weird conceptual things, but for the most part, uniform distributions kick a lot of ass because they're just areas of rectangles, right? One last question about this. What's the probability that x is greater than 12? Greater than 12.
7.
Whatever, like 5 out of 12 is.
Let's see, here's 12 roughly, right?
So wouldn't you find?
Greater than 12,
Just be 5.
yes? Do you see that? Because I can't get 20, so greater than 12, it's sort of like me saying roll a die was probably get a greater than 5. 1 out of the 6. What about 7? Well, it's not on the die. It's not even something that could happen. So greater than 12, that only goes up to 19. So do you see how that makes this box here? Greater than 12, 12 to 19. So what's the width? 7? 7 over 12. Which is whatever the hell it is. I think it's 0.58? 0.583? All right, how y'all doing? Couple of weird spots, but just remember, if I have a continuous distribution and I have the picture, and the total area is 1, the answer to any question is the area of the slice it cuts. That's it, right? So what slice did this question cut? From 12 to 19, find the area, you're done. That's how every continuous distribution works. Now, just to give you an example of a type of continuous that we're not going to do, but just to show you, there are triangular distributions.
Is that only for uniform?
Say again?
Is that only for uniform?
No. Any continuous distribution, if you have a picture of it and the total area is 1, the answer to any probability question is the slice it cuts out, the area of that. So if I have a triangular distribution, we're not going to do this, by the way. Just want to show. Don't even draw this. Don't even write this down. And I want to know the probability from here to here. Does anyone know what shape that is? That I just carved out? Trapezoid. So then I would just find the area of that trapezoid. Done. Right? So I just want to show you that because no matter what continuous distribution I have, no matter what the shape is, I just find the area that my question carves out. And I'm done. Because area equals probability. Just like the bullseye thing we talked about. Okay, maybe. Okay. This is what I was talking about earlier. I'm going to show you the formulas for the mean and the standard deviation of a uniform curve. Uniform distribution. Math people are weird. Straight line, but we call it a curve. So here's the general way you could be given a uniform curve. Either I'll say it's a uniform probability from blah to blah, or I could just say U, just like I did over there, right? Really quickly, what would the height of this be?
1 over B.
No? How wide is this? How did you know this was 12?
B minus A.
Yes, so this is B minus A wide, so how tall is it?
1 over B minus
1 over B minus A. Don't freak out. You don't have to memorize that shit, right? That's just what it looks like in general. If I don't know the specific numbers, right? So if I'm given a uniform curve, let me ask you guys this. For this specific nice concrete example, what do you think the average is? It could be anything from 7 to 19, but they're all equally likely. So what do you think the average is? Where do you think the average is? Where should the average be sort of close to in general?
In the middle.
In the middle. Okay, now think. They're equally likely. There's no reason, if it was like this, it would be closer to that side because that would be heavier weighted. Like they're all equally likely. So what is the average?
13.
How'd you get 13?
Mhm.
In the middle. Yeah, so you can either add 7 and 19 and divide by 2, or you can just figure out what's in the middle of those two. Does that make sense? The average is in the middle. I love it. So how do I represent that in general? It would just be A plus B divided by 2. That's the mean. So let me say this again for, I don't know if I said this before everybody got here, but you're gonna see formula, you're gonna see questions in the homework that talk about the average and the standard deviation of a uniform probability distribution. There was a lot of words in that sentence. You'll see formulas, you'll see problems in the book that ask you for these for a uniform. I'm not gonna worry about too much, but you still gotta do the homework. I want you to know they exist, and you just gotta plug and chug, right? Now let me get your reaction to this. Here's the standard deviation formula. I wanna know what your reaction is. So first thing, say again? Oh, see, I live for that shit. I'm sorry. Glad the class didn't say that. I was disappointed. It's the first damn thing I would say if I was like, why is it freaking 12 down there? So a lot of the stuff we use, a lot of the formulas we use in here, when I can't show you the derivation, it's because it requires at least Calc 1, if not Calc 2, Calculus 2 to do. So we just use the damn formulas and we let those crazy fools prove it for us, right? Those people being me. I could show, if you're curious, if you know some calculus, I actually could give you a handout showing you the derivation of this, and then you can see exactly where 12 comes from. Okay, so if you just let me know, I can even post it up on Canvas, so if you could look at it if you want to. Just remind me, and I'll do that. Okay. It's a neat little derivation. But for the rest of us, for example, how do I figure out, so that guy's mean over there, this guy, his mean, 7 to 19, his mean is 13, right? What's the standard deviation? It's gonna be the square root of 19 minus 7 squared divided by 12. The neat thing about 19 minus 7 is it's 12 squared divided by 12. 1 12 cancels, square root of 12. It's twice square root of 3. Someday I'll memorize square root of 3. It's like 3.53. I'm making shit up. Somebody help me out.
46.46.
What is it?
3.46.
3.46? Something? Yes.
So for the standard deviation, is it always 12 on the bottom?
For a uniform distribution, yes. And again, there is reasoning behind this. It's just a whole lot of work, and then the 12 just sort of like comes out of the work. There's nothing magic about 12. Yes.
Would A and B ever be like decimals?
Totally. There's a problem in the homework, I think, that they're decimals. Okay, all right. So here, I've got a worksheet that I want you guys to do. One side of this worksheet has like a Mayan pyramid on it. Don't worry about the pyramid side yet. Do the other side. That looks a little more boring. So it says binomial and uniform. So maybe try number 2 first, because it's the uniform example and we just talked about it. And the first problem is a binomial practice.